Imagine you're trying to map this infinite, invisible landscape, and the only landmarks are the prime numbers themselves. You'd want a really, really good ruler, right? Something reliable to measure your way through the chaos. But what if the most elegant, most perfect ruler ever designed was fundamentally broken? Well, today, that's exactly the tool we're going to talk about. All right, let's just dive right in. The biggest treasure map in all of mathematics is the one that explains the prime numbers. You know, those numbers that are the building blocks for everything else? The famous Riemann hypothesis says the secret to their pattern lies with the zeros of a special function, the zeta function. If we can just prove that all those zeros fall on one single straight line, we crack the code. But, how do you even start searching in infinite line? Well, mathematicians came up with this absolutely ingenious ruler using something called gram points. Think of them as perfectly spaced tick marks that promise to neatly catch every single zero, one by one. It was a beautiful system, it was simple, and it worked. Until one day, it didn't. Okay, so to understand this ruler, first we have to get a feel for the landscape it's measuring. And here's a little secret. We're not actually looking at the zeta function directly. We're looking at its shadow. Now, don't let the symbols freak you out. This is the Riemann-Siegel z function. See, the original zeta function is complex. It exists in this world with real and imaginary parts, which makes finding its zeros a real headache. This z function, though, is a clever trick to make the whole problem way, way simpler. So here's what it's doing. It basically takes the spiraling, complex values of the zeta function and rotates them just right so they all land flat on the real number line. Instead of some complicated spiral, we get a simple wave that just goes up and down. And finding zeros now? It's as easy as seeing where that wave crosses the line. It's a total game changer. And what's the magic ingredient doing all that rotating? It's this function right here, theta of t, the Riemann-Siegel theta function. You can think of it like a compass. As we move up that critical line, it tells us exactly what angle the zeta function is pointing at. And understanding this angle, well, that's the key to making our ruler. Yeah, seriously, think of it just like that. As the zeta function spirals around, theta tells us precisely how many degrees, or radians, it has turned. By knowing that angle, we can pick out these perfectly evenly spaced marks for our ruler. And this leads to a really elegant solution. So, with these tools in hand, mathematicians back in the day developed what really seemed like a perfect, simple rule for finding every single zero, one after another, in perfect order. They defined something called a gram point. A gram point, G-R-A-N, is just a spot where that theta function, our compass, hits a perfect multiple of pi. You know, a perfect half turn, or a full turn, or a turn and a half. They become these incredibly predictable, easy-to-calculate markers along the line. And here's where the magic really happens. When you plug a gram point into our z function, that whole rotation part of the formula, the e to the I theta t part, simplifies down to just -1 raised to the n, which means it's either going to be +1 or -1. That's it. Suddenly, this complicated function becomes incredibly simple at these specific points. And this creates this beautiful, predictable rhythm. At one gram point, the function should be positive. At the very next one, it should be negative, then positive, then negative. And think about it. If a continuous function is positive at one point and negative at the next, it has to have crossed zero somewhere in between. There's no way around it. This pattern was so reliable, it got a name, Gram's law. It was this simple, powerful promise. For every single gap between two gram points, you'll find one zero. Exactly one. No more, no less. Suddenly, the hunt for zeros wasn't a wild goose chase anymore. It was systematic. And just look at how perfectly this works in the beginning. Between G0 and G1, the signs flip from plus to minus, and bam, right in between is our first zero. Between G1 and G2, it flips back, and there's the next zero. It's just perfect. For the first 100 or so zeros, this ruler is absolutely flawless. But this is mathematics. And any law that's just based on observing a pattern is really just a theory waiting to be broken. And oh boy, was this one about to break. After you see a pattern that perfect, you have to ask yourself, right? Could it really be this simple? In the messy, chaotic universe of prime numbers, is anything ever really that neat and tidy? The answer, of course, is no. And the first little crack in this perfect ruler shows up at the 126th gram point. So here it is, the failure. At gram point 125, the function is negative, just like it's supposed to be. So at the next one, number 126, it should have crossed the axis and turned positive. But it doesn't. You run the numbers and it's still negative. The expected sign change, it just vanished. This was a shocking discovery, and it has a name: Lamer's phenomenon. This was a huge moment because it proved that this simple, elegant ruler that everyone was counting on had a crack in it. It wasn't a law after all. And the consequences are profound. For the function to be negative, then negative again, it had to have dipped down, crossed the axes twice, really, really close together, and then popped back down again, all inside a single gram interval. That means the next interval got skipped entirely. It was just empty. The perfect 1-0 per interval system was completely shattered. So the ruler is broken. It fails. And it turns out it fails infinitely often, which leads to the obvious question, why on earth do we still use it? It really does seem like a paradox, doesn't it? If your tape measure sometimes missed numbers or added extra ones, you'd throw it out. But in mathematics, a tool that breaks in a predictable way can actually be even more useful than one you just assume is perfect. And that's the absolute key. We know how it breaks. Modern computer algorithms still use gram points as the basic grid to search for zeros, but they also use what we learned from Lamer's phenomenon to double-check the bad neighborhoods, the spots where the rule is likely to fail. The failures aren't just mistakes, they're signposts telling us where to look closer. The broken ruler is still the best map we've got. And this whole thing leaves us with a really fascinating thought. The story of gram points isn't just about math. It's a story about how science works. It shows how a simple, beautiful idea can be an incredibly useful guide, even when it's not the whole truth. In fact, its imperfections are what force us to look deeper. And it's there, in the exceptions to the rule, that the most profound discoveries are almost always hiding.